Just record. So we can move. Okay, so like I said earlier, so let's say we have a message. We have a message. And then this is transmitted. And here we are expected to receive an estimated message. So the idea is that we are not certain what is going to happen within this dimension. Okay? Because we are going to deal with some form of circuits or circuitry devices. And they are going to introduce some level of distortion in this process. But along the line, depending on the mode of communication or the channel mode, it could be wireless or wired, okay? So it means that this signal may end up moving off through some other means, and the interaction could further distort the signal. And let's assume I sent a signal, say something like this, probably a sinusoidal signal. Then it goes up and now begins to interact with other signals, okay? With some noise, okay? And all the way. So now this is the channel, a whole lot happens. Then along the line, at the receiver, and I receive something that looks like this. Okay. Now, this is the analog world, right? This is analog. This is also analog. This is what we are going to interpret. So probably this is my voice message, right? Okay. Well, my voice message wouldn't have been as clean as this anyway. So because of the pitch, the tone and all, it would have looked something like this at the transmitted end. Now, so the idea is this. At this point, this is my analog world. Also at this point, this is my analog world, right? So it's at this point, I actually appreciate what was transmitted. Okay? And depending on the nature of information, we may not want to transmit over the interface just the same way, much like, or more like every other, the same way other messages have been transmitted. So depending on, you know, the level of confidentiality that is sought after. So we may want to bring in some cryptographic technology, right? So security becomes a major deal. And information theory is the hub here, okay? Because we want to encode the information in a way that nobody will be able to decode it. So it means that my encoder and my decoder will have a certain information. Probably they share a certain key. And it's only with that key that you can use to access that message. Okay, so probably I transmit a 0101, and at the instance of transmission, then it becomes A box $, K V 0 B P Z, then something like this. This doesn't make sense anymore. Now, this doesn't make sense anymore. So if this now leaves my encoder, so it means that my decoder will have to possess the information, or better still, an algorithm that will be able to decode this to say, well, what was transmitted is 0, 1, 0. Okay? So we're also doing some information theoretic activities while, encrypting or decrypting, okay? But the point is, for us to be able to do this, we must come to the digital plane, okay? Now, in coming to the digital plane, we already know that we have to do some form of switching. So we have to do modulation, okay? So we have to modulate, okay, using any of the known digital modulation techniques. So, and then we're able to map this entire analog sequence to our digital equivalent. But this is what we are now saying, that once we do this, we already mentioned two aspects to our coding scheme: source coding and channel coding. And as we'll see shortly, we could run an entire communication system where the source coding and the channel coding will be done separately. Or better still, we could have a joint source channel coding scheme, okay? Now, let's assume our source channel coding and source and channel coding is a joint process, okay? Then it means that at this point, we'll have an encoder that will encode this message. And once it encodes this message, we call this the encoder. So at this point, we can now say, well, what is going to be the output of this encoder? So let's assume the output of this encoder is some symbol sequence S to the power of n. Now this goes through the channel. This goes through the channel. I will say this is the channel. And we know that the channel is going to relate the output sequence. So if it receives this, then it means we must have an output bit sequence. And for us to have this, then it means that the channel itself, more like in your signal processing or signals and system, must have a property that relates the output with the input. Okay? Now, for us to be able to do this in signal processing, we say, well, we have a system, the input goes in, the output goes in, then whatsoever we have here, if this is X, this is Y, then this gives us some information that says, well, this is the channel impulse response that characterizes the channel, okay? Now, this impulse response, therefore, can be derived through the system transform, or better still, the through the system response. Yeah. So, and then for us to be able to do that, we take the ratio of the output to the input. Okay, and we'll say that is the transfer function, right? So if we now say the transfer function, then we can take the Laplace transform of this and of this, and then take the ratio of y to x, and then we say that gives us the channel response or the transfer function of the system that characterizes this system. But now in information theory, we also have the same thing, but there is a metric that now gives us some information about the input relative to what was received. And that is what we call the probability transition matrix. Okay? And that gives us the conditional probability that we will receive y given that x is transmitted. Okay? Now that we have this, recall that y super n is not what was transmitted. We transmitted m symbols. Okay? M symbols, after encoding m symbols, we got a sequence, S super n. So the point is, once we have this from the output, we will now have to decode this process. So we now have our decoder here. Once we decode the y super n sequence, then we should get an approximate value of what was transmitted. Okay? And then we say, well, does this message look like what was sent? So because we are not sure, there may be distortion depending on the type of channel. There may not be distortion, but there is a metric that tells us if there will be distortion or not. So this is what brings us to that concept we'll be talking about, which is your channel capacity. Okay, which has to do with what's going on in this part of the block. Okay. And if we assume that the channel is memoryless, that is, the probability distribution of the output depends only on the input at any given instant of time. So it means it has no memory. So it means that if, for instance, we transmit a 0, then we should receive a 0. So if S super n is the same as a 0, then Y super n should give us a 0 on transmission. So it means that whatsoever we transmit is received, such that the probability P, the output probability P of Y is strictly dependent on the input probability or the source probability, such that we now have the conditional probability that we'll receive Y given that X was transmitted as the characterization of the channel. So it means that this probability transition matrix, this parameter, is the probability transition matrix, is what gives us the information what gives us the information about the channel in terms of its resilience to errors. Okay. So it means that depending on this distribution, we should be able to tell if certain bits were received in error or not. Hence, going by what we already mentioned earlier, it means that the information capacity of a discrete memoryless channel is defined as C being the same as the maximization of the mutual information between X and Y given the input probability or over the input probability distribution or source probability distribution. So the idea now is this. According to Shannon, we have that the information channel capacity, C, is the same as the operational channel capacity. Now, be that as it may, it means that we were able to achieve data compression by removing redundancy. And now we want to achieve data transmission by adding redundancy. Why is that? Because we want our message symbol to be robust against channel noise. And if that's what we want to achieve, so the bottom line is we actually want to develop error control codes. That's why we add redundancies. Okay, codes. That's the need for adding redundancy. Well, if we've given a brief background, so let us look at some channels, okay? Because we said this channel matrix will tell us if we've got to deal with, or if we have to deal with some errors or not. So let us look at a few channels here. So we have the noiseless. We have the noiseless binary channel. Here it means that if we transmit, say, a 0, we should receive a 0. Okay? That is, this is X1, then we should get Y1 here. And if we transmit a 1, we should get a 1. X4, X2, Y2, all the way. So it means this is noiseless because the distribution here will give us the probability that we receive Y1 given that X1 was transmitted. And the channel matrix here will give us the probability, the conditional probability of receiving Y2 given that S2 was transmitted. And from this, it means that the channel matrix will therefore be given in this format. So we cannot describe this. So here, so let's say this is my Y1 column and my Y2 column. This is my X1 row, and this is my S2 row all the way, okay? So it means here we have, by this distribution, probability of y1 given x1. And here we have the probability of y1 given s2, right? And here we have the probability, this column of y2 given s1. And here we have the probability of y2 given s2. So going by this noiseless channel, so the probability transition matrix that describes what is going on in this channel, therefore, will be given as the probability of receiving y1 given s1 is given. So now the probability of receiving y1 given s2 is not here. So it means that's going to be a noise. So if it was a noisy channel, we are going to have a parameter for that. Now, the probability of receiving y2 given x1 is also not available in the noiseless channel. So this is a 0. And then the probability of receiving y2 given s2 is available. So in other words, this gives us a full description of a noiseless binary channel where we cannot probably associate any symbol to be received with some level of noise ratio. Let's put it that way. So it means that the probability of receiving a bit in error is 0, largely because all the bits are received as sent. Okay. Now, is this clear before I move on? Is this clear?
Yes, we can move on, sir.
Okay. Then, okay. Then we equally have a noisy channel with overlapping output binary channel. Okay, but this is tricky. We call it noisy, but it's really not noisy, okay, because the channel appears to be noisy. So this is more like a single input, multiple output channel. Let's assume we transmit a 0, and then we have two possible outputs. Output 1, output 2 for the 0. This is our X, and we're expected to receive a Y. And when we transmit a 1, then we also expect two possible outputs, 1, 2. So this channel has two possible outputs corresponding to each input, okay? And you'll observe that it appears to be noisy because for the binary symmetric channel, as we'll see shortly, you see that given an input, should we have multiple outputs, that gives us some a little reason to be worried. Okay, because the noiseless binary channel we know is such that should I transmit a 0, I should get a 0. Okay. Now, this is just one channel. Now we have the binary symmetric channel. Now, for the binary symmetric channel, it means that should we transmit a 0, we should get a 0. And should we transmit a 1, we should get a 1. But there is another possibility of receiving a 1 when we transmit a 0, or better still, receiving a 0 when we transmit a 1. So a channel that looks like this is called a binary symmetric channel. And this channel is such that we have x1 here, then we should receive y1, we have s2 here, we should receive s2. So looking at the probability transition matrix, so this is the probability of receiving y1 given x1. Now, this is the probability of receiving, no, sorry, this is y2. Y2. Of receiving y2 when x1 was transmitted. So we know this is an error in this distribution. And now this is the probability of receiving y2 when x2 was transmitted. That's meaning accurate reception. And now this is the probability of receiving a y1 when s2 was transmitted, which is an indication of error. Okay. And going by our previous analogy, then we can put up, or better still, describe the channel matrix in this case. Now, for our channel matrix, it means that the output is going to be the same as the probability transition matrix. These are matrices times the input matrix, right? Let's say this is the probability of y, the probability of the y. So this is the channel matrix. So it means that given the input and the channel distribution, we can get our output. So we already know from the description we gave earlier that we have the y1 column here, y2 column. It could be as long as whatsoever, depending on the size of the square matrix. And then we have x1 row and s2 row. So it means that at this point, we have the probability, the conditional probability of receiving y1, given that x1 was transmitted. And here, the probability of receiving y1, given that s2 was transmitted. So all of this and this comes to this output, right? So the probability of receiving y1 given s1 and the probability of receiving y1 given s2. And here also we have the probability of receiving y2 given x1 and the probability distribution of receiving y2 given s2. Then here we can now multiply by the input, we have two inputs, probability distribution of S1 and the probability distribution of S2. And once we perform this operation, we are going to get the probability distribution P, Y1, which is the output, and the probability distribution Y2. Now, this gives us the channel matrix for the binary symmetric channel. And going by this, we should be able to resolve a few problems, okay? Which I will reserve, you know, probably we'll solve some of those after, probably after this class. We'll just try to, let's look through and then we'll solve a few numerical examples much later. Though we have some numerical examples in the lecture notes online. And then one other channel we also want to deal with. Now you observe that in this case, both the corrupted symbol and the actual symbol are received, okay? But there's also a type of channel that this component is erased, okay? So we'll call it the binary erasure channel, okay? So it is more like the binary symmetric channel in which some bits are lost rather than corrupted. So you see that in this binary symmetric channel, the bits, some of the bits are corrupted. Okay. But in binary erasure channel, let's look at it. We have that a 0 is transmitted, then a 1 is transmitted and also received. But here, we now have that there is an error ratio. Now, the point is, this channel gives us the erased symbol. So if this is 1 minus alpha, and this is 1 minus alpha, then this is alpha, and this is alpha. So in this case, we now have to deal with a different system. So in your digital computer technology, you talk about lost packets. Then you at times you also talk about corrupted packets, right? Corrupted packets. Well, let's not go in this dimension because at the end of the day, your packet is just some bits with some header, right? With some headers, okay? Because your bits, we're talking in the physical layer. Then you have the data link layer. Then you now have your network layer, right? I think that's your layer 3. That's where you talk about packets. So here you talk about bits. Here you talk about frames. Then here you talk about packets. Then in your transport layer, you talk about segments, right? Then all the way above, we deal with data, right? From your application presentation session, right? So this is the lower part of your OSI model. You must have, well, you still do this in your computer technology, OSI model. So here we have the application layer, the presentation layer, and the session layer, right? So here we deal with data. So here we are dealing with bits, right? So we are dealing in the physical layer. That's where we are. But when you now begin to go up the layer and then you are using your routers, you are somewhere in layer 3. So it means that there are some headers that have been added and trailers or whatsoever you call them. This is for the frame, this is for the packet. So it means that these headers just turn my bits to packet. So this header from my data link layer turned it to a frame. So that there are times you get to see that, well, suddenly they're just saying frames, or they are talking packets, or they are talking segments, or talking bits. So, but now that we are talking bits, we are in the physical layer. Okay, so I want you to get that. That's by the way. So, but what we are trying to say here is that in this binary erasure channel, BEC, some of this, rather than being corrupted, they are lost. Okay? And the interesting thing is that the channel knows the bits that have been erased. Okay? So here we now see that the binary erasure channel has 2 inputs, but 3 outputs. Unlike the binary symmetric channel where we have 2 inputs and 2 outputs. Okay? Okay. And a typical example now would be, so let us assume, let's just wipe a few things from this. Let's clean this up, clean this, clean this. So let's wipe this, wipe this, wipe this, and wipe this. So I'm going to wipe all of this. So let's assume we have P here, 1 minus P, 1 minus P. Okay. So we have, so let me withdraw this. So let's make it a little nicer than this. This is X1, S2, so this is P, this P. So this is Y1, Y2, Y3. So we have 3 outputs. So going by this, we can easily tell that, let's describe the transition probabilities. This is going to be the probability of receiving Y1, given that X1 was transmitted. Why this is going to be the probability of receiving Y2, given that X1 was transmitted. This is going to be the probability of receiving Y2, given that S2 was transmitted. And this is going to be the probability of receiving Y3, given that S2 was transmitted. Okay? And now the transition matrix is going to follow directly, which is P, Y given Xi. So this time we have Y1, Y2, Y3. So we have, those are the columns. Then we have row S1 and S2. We have 2 inputs, right? So in this case, we are going to have the conditional probability of receiving Y1, given that X1 was transmitted. Then the probability of receiving Y1, given that S2 was transmitted. The probability of receiving Y2, given that X1 was transmitted. Probability of receiving Y2, given that was transmitted, the probability of receiving Y3, given that X1 was transmitted, probability of receiving Y3, given that S2 was transmitted. And going by this, what do we have here in the binary erasure channel? Y1 given S1, that's 1 minus P. Y2 given Y1, that's P. Y3 given Y1, it doesn't exist, that's 0. Then Y1 given Y2, it doesn't exist, 0. Y2 given S2, that's P. And Y3 given S2, that's 1 minus P. So this is the channel, the transition matrix for the binary erasure channel. And you see, this is completely erased and this is completely erased, and it knows that those were erased. Okay. And then if we now want to complete this matrix, then you know we have three output probability mass functions or distributions: P of Y1, P of Y2, P of Y3, and here we have P of X1, P of S2. And then you could play with some examples, and we also have that. Yeah, I think that's about it. That's about it. So now that we have talked about, you know, some types of binary channels. So we know we have the noiseless, the noisy, the binary symmetric, binary erasure channel. Let us come back to the capacity of this channel, okay? Because so far you see that at this point, should I transmit a 0, I'm supposed to receive a 0. So the capacity of this channel is actually 1 bit. Isn't it? Are you with me, please? I'd love to hear your input this time.
Yes, we are together, sir.
Okay, that's fine. That sounds good. Okay, so let us now go back to the channel itself, because looking at this, at the input side, at the output side, at a given point in time, we can receive 1 bit, you know, and we can transmit 1 bit. So it's logical to say, well, the capacity is 1 bit. But what if we want to extend that capacity? Then we need to do something about it. So that will bring us to modulation, right? And then when we come to modulation, we know we have single carrier, and multi-carrier techniques. So here you can mention your regular binary phase shifting, quadrature phase shifting, quadrature amplitude modulation. These are in use in your WiMAX, techniques, and some, even in your OFDM, we use this to modulate the subcarriers, right? Yeah, even in your 4G, we still use them, okay? And then here we have OFDM, orthogonal frequency division multiplexing, where we now have subbands, okay? Because here we run into intersymbol interference, okay, issues. So because we are dealing with a wide band, but this time we want to deal with narrow bands, okay, narrow channel bands, okay. So put any subbands, and then we are able to mitigate intersymbol interference. So in this case, as we'll see shortly, you see that, well, the block length is very large, okay? But in this case, the block length is not all that large, but relative to the channel size, okay? And then we now do some kind of cyclic whatsoever and all of that. But we leave that for digital signal processing class. So let us come back to this. Because at that instance, at the point where we want to increase the number of bits, we actually want to improve on the data rate, on the pure theoretical note, and the actual, say the throughput, right? What is achievable in reality, yeah, in relation to your data rate. So that's fine. So if we know what the capacity of these channels that we've been talking about is and all of that, so how do we describe the properties of the channel capacity itself? When we talked about entropy, mutual information, we made mention of some of their properties, and the channel capacity itself follows directly, because we already know for the binary memoryless channel that the channel capacity is the same as the maximum value of the mutual information over the input distribution or the source distribution. Hence, since it is dependent on the mutual information, we already know that the mutual information is a positive value. It can't be a negative value. It's a non-negative value. So hence, one of those properties is that the channel capacity also is non-negative, since the mutual information is non-negative. Okay? Now, the mutual information is, let's make that our second point. The mutual information is a continuous function. It's a continuous function of the probability distribution, input probability distribution, or source probability distribution. Now, also, the mutual information is a concave function of the source probability distribution. So another point is that the channel capacity is less than the log of the mod value of our source symbol, since C, the maximum, is the same as the maximum value of the mutual information, which is less than or equal to the maximum value of the source entropy, which is the same as the log of our source distribution. And then, in a similar vein, in relation to the output symbol, we have the same description. Okay. Now, if this is clear, we'll come back to this shortly. Then we can now provide a formal statement for the channel coding theorem, because we already know what we can transmit over this channel, okay? And now we also want to provide a formal statement to this, because we know that by what Shannon postulated, that the channel capacity must be greater than or equal to the rate at which we want to transmit over this channel. And then the rate in this case has to do with what we can transmit, the bits we can transmit, okay? And now, what did Shannon actually say? Let's just provide a brief note here. Now, Shannon or Shannon's theorem says that it is possible in principle to devise a means whereby communication system will transmit information with an arbitrarily small probability of error, provided that the information, right, R is less than or equal to a rate C called the channel capacity. And this technique is used to approach this end known as coding. Okay? So technically, the theorem, let's wipe this. Technically, putting this theorem in this perspective, say, given a source of m equally likely messages with m far, far greater than 1, which is generating information at a rate R, given a channel with channel capacity C, then R is less than or equal to C, or if, let's say, if, let's put it more appropriately, then, if R is less than or equal to C, there exists a coding technique such that the output of the source may be transmitted over the channel with an arbitrarily small probability of error. Small probability error of receiving the message. Okay. And therefore, we can now provide a formal statement that negates this. Okay, because we can now say, well, that's a negative statement associated with Shannon's theorem. Okay, and so conversely, given a source of M equally just the same way we describe this, equally likely messages with M far greater than 1, which is generating information at a rate R given the channel capacity C, then if R is greater than C, then the probability of error is close to unity for every possible set N transmitted symbols. And there we say that this probability of error is bounded, right? Okay. Now, this is more like a formal description, okay? That we can actually design a code for this message symbol. That's the beauty. So, going by what we already described in our notes, we now have that for a discrete memoryless channel, all rates below capacity C are achievable. Okay? So this actually means that for every rate R less than C, there exists a code or a sequence. There exists a sequence or code 2 to the power of NR N with maximum probability of error, say lambda N being the same as 0. Okay? So it means that such a code as this can be designed. Let's change this color. When the rate is less than the capacity of the channel. And remember that this rate we already related with the compression rate, which is our entropy. Okay? So the channel coding theorem therefore promises the existence of some block code, NK block code, okay, which we are going to be talking about shortly. We're going to talk about some of those block codes and convolution codes, even turbo codes and all of that. So what the channel coding theorem infers is that some NK block codes exist so long we are able to achieve this rate for a sufficiently large N, where N is the block length, okay?
All right.
So for a sufficiently large block length, we can actually design a block code that will be able to transmit over this channel should R, the rate, be less than the channel capacity. And we know that this block length is the same as our code word, which is, because the encoded number of bits, which contains both the message bits n minus k, message bits, and the parity check bits. So this entire length is n, okay? So we have the k here as the message bits, okay? Message bits. So n minus k is the parity bits or the redundant bits, okay? So the length of this code word, I said code work, is supposed to be code word, not code work, please. It's not a code book, code word. Word, yes, code word. Okay. So once we have this message bit, so looking at this, so we can relate this to the message bits to the power of NR. Okay. Think that's about it. And then we now want to look up some other details. And for us to be able to do this, there's something I just need to mention. Okay. So okay. So since I already mentioned that such codes can be designed going by this description from Shannon, now let us provide another statement here. So we can now say that an NK code, for instance, for the channel, say, given the input sequence, then the channel matrix, and then the output sequence will consist of the following. We know that this is the block length, n, and the message bit k. So a code for this channel, as we already described, will consist of one, an index set, say 1, 2, all the way to k, okay? And then it will also contain an encoding function where we have x to the power of n for the input symbol, the indexing, okay, or to k, then to give us the output, what we expect, okay? This gives us that code word. Leading code words. SN1 with the index XN2 all the way to SNK, right? And by the time we combine these code words, we now have a code book. So in other words, a code book consists of a set of code words, right? So we have the index set, we have the encoding function, then we also now need the decoding function. A decoding function. Say G, given N, will now lead us to 1, 2, all the way to K. Okay? Now, and this can be determined, you know, with some level of certainty. Okay? And now that we have this, therefore, the rate of this code, R will now be given as log K over N bits per transmission. Okay? Because we have the message bit and the block length. Okay? And we already know that 2 to the power of NRN codes will exist. This sequence will exist so long the probability of error reduces to 0 as the block length becomes sufficiently large. And the block length will only become sufficiently large when we have some parity check bits added. And the parity check bits, therefore, will be used for error control. Okay? Let's not forget this. Okay? That is very, very important. Because when we now go into error control codes, we talk about Hamming codes with Solomon, Golay codes, and all of those block codes. Then we also talk about convolution codes, and because the most basic technique for decoding is the joint typicality decoding. But for effective decoding, we do maximum likelihood. And that will bring us to V-tab decoding when we begin to talk about convolution codes, okay? Well, for joint typicality decoding, it's more like it's straightforward. We have the sequence, and then once we transmit, then the output and the input need to be aware of what is being transmitted, and then as such, we are able to get by. So, but for maximum likelihood, then it's more sophisticated, then we have to run some algorithms, okay? And I already mentioned that both the source encoding and channel encoding could be done separately, or it could be a joint system, okay? So I think this is more like providing a brief overview of channel capacity. So I think we still have a few minutes. I'll just probably solve, let me look out for some examples that we don't have already in the videos. So just, since we are recording, then we just need to do something new, okay? Okay, so, okay, is this going to be worth it? Okay, let's look up a simple example. I want to look up one simple example from the materials I have before me, and then we just get by. Okay. Something that won't take much of our time. We have just a few minutes. Let's wipe this. So let's assume we are given this channel transition matrix, 0.9, 0.2, 0.2, 0.1, and then 0.8. And then they want us to do a few things. We can draw this channel matrix, that is not a problem. And then they want to evaluate the mutual information. And once we are able to evaluate the mutual information, we already know that the channel capacity is the maximum value of this over the distribution. And what is the associated with the output, assuming equiprobable inputs? So in this case, they want to assume equiprobable inputs. So the implication, therefore, is that P of X1 is the same as P of S2 is the same as 1/2, which is 0.5, right? That's the implication. And we know that the channel matrix is the same as P of Y1 given X1, P of Y1 given S2, P of Y2 given S1, P of Y2 given S2 is the same as 0.9, 0.2, 0.1, 0.8. And from this, we know that this is a binary symmetric channel that looks something like this, right? Where this is 0.9, this is 0.8, this is 0.2, this is 0.1. We have X1, S2, Y1, Y2. Okay, so we have this is this upper part, this is this lower part, then this Y1 given S2, that is this, as Y1 given S2, that is this, then Y2 given S1, that is this which is 0.1, right? Now, for us to be able to resolve the mutual information, we already know what to do. What is the mutual information? What's the expression for that? No, we could use the relative entropy formula, whichever way you are able to resolve this. And you could also use the chain rule, solve for the input output entropies and the joint entropies, and then you then just pull out the difference and you are good to go. But let us use a more general approach, XY, but whichever way we are going to get the same answer. So this is the joint distribution. Log to this too. Y, J, or let's just put it as XY. So this is what we have, okay? And if this is correct, recall your base rule. So where we have the joint distribution being the same as the product of the conditional distribution. This with the output, and is the same as y given x, then the input. So if we compare these two, since they are the same, that's P of x given y, P of y is the same as P of y given x, P of x. So it means that we have P of x given y divided by P of x, right? Is the same as P of y given x over P of y. So if we cross multiply, we come to this still. So these two are the same, right? Then it means that we can now plug the same expression into this, and then we are good to go, right? So it means that this expression and this expression are the same. So from this point, we can now say that the mutual information is the same as the summation xy. Now, by base rule, this expression is the same as this. So either of this. So, and we know this is a transition matrix. P of y given x, right? So we can replace this expression by this expression. And we have the input probabilities, okay? 0.5. So P of y given x times P of x log. Now, we already know that this entire expression is the same as this, so we can replace that with 2 base 2, the channel matrix, divided by the output. Okay? And we know that the output, P of y1, P of y2, is the same as 0.9, 0.2, 0.1, 0.8 times 0.5, 0.5, right? Because it is equiprobable, the input. So these are the input probabilities. So from this, we can resolve that P of y1, P of y2 is the same as this times this. That will be 0.5 times 0.9 plus 0.5 times 0.9 plus 0.5 times 0.2, 0.5 times 0.2. That's done for y1. Then y2, then this times this row times this column, rather. That will be 0.5 times 0.1. We're just doing matrix multiplication plus 0.5 times 0.8, 0.5 times 0.8. So what do we get? So this is going to give us 0.55 and 0.45. Now, according to the rule of total probability, this should give us, it should be the same as 1, right? The sum of output probability should be the same as 1. So if we add 0.55 plus 0.45, what do we get? That's 0. That's 5, then that's 0.1. So it gives us 1, so it's correct. Is that clear? Is that clear, please? I'd love to get your feedback, please. Is it clear?
Yes, you can continue, sir.
Okay. Okay, now that we have done this, so we have all these parameters. We have this is here. This is P of y, x. Let me use another color. This is the transition matrix. Now this is the input probability distribution. And here we just got the output probability distribution, right? And that gives us all the parameters we need to resolve this. So all we need to do is to plug in all the parameters, and then we are good to go. And now we can expand the entire process. So the mutual information will be the same. So for the first point, that's 1, 1, right? So we have P of y1 given x1 times p of x1 log to this 2 p of y1 given x1 p of x1. So that's the first thing to do, plus p of y1 given s2 p of s2 log to this 2 p of y1 given s2 over p of s2, right? Then plus p of y2 given s1 p of x1 log p of y2 given x1 over p of s1. Then plus p, that's this 2, p of y2 given s2 p of s2 log to this 2 p of y2 given s2 over p of y2, right? So once we plug in all of those parameters that we have here, so let's wipe this. Then let's just do this here. Then we should have our mutual information to be the same as 0.9 times 0.5 log to this 2, 0.9 divided by 0.55 plus 0.2 times 0.5 log to this 2, 0.2 divided by 0.55 plus 0.1 times 0.5 log to this 2, 0.1 divided by 0.45 plus 0.8, 0.5 log to this 2, 0.8 divided by 0.45. Now, do recall that we have our base 2 here. So if your calculator cannot operate, resolve this operation, then you have to do a base conversion. So it means that this entire expression, so let's just explode this. This entire operation will look something like this. So you repeat this for everything, 0.9, then 0.5, then to multiply this entire process, log to this 10, 0.9 divided by 0.55 divided by log 2 base 10. So you're going to do a base conversion for all of these, right? For all of these. So once you do that, then you're going to get the mutual information. To be the same as 0.3197 minus 0.1459 minus 0.1085 plus 0.332, which is going to give us 0.3973 bits per symbol. Okay. Well, this is a really simple, basic problem, but in the question bank, I'll try to solve some more complicated problems that will be typical of learning. And there are quite a number of examples I have here, but I think this is a good place to stop. We are just a minute away from our class time. So any question, please?
No questions, Abed. I think having more examples will really help us.
Okay. So,
and I also want to ask, this is Shannon. Can we have the book? It's something that cannot be missing in our life.
What's that? I didn't get that.
the Shannon textbook where he did all this work.
Okay, the classical paper. Yeah, I think
Yes, sir.
we could download that online.
Okay.
Yeah, it's available online. If you're unable to get it, just let me know, then I'll get it. I'll pass it across. Yeah, it's original paper. Mhm.
All right.
That's fine. So in the absence of no other questions, so I think we'll call it a day, and we'll meet on Friday.
All right, sir. Have a nice day, sir.
And you too. So bye for now.
Thank you and good night.